All right, so today's video is going to be about work done by non-conservative forces, all right? This is a big section. There's a lot going on here, all right? So let's dive right in, all right? So earlier this unit, or maybe last unit, we learned that work is done by a force, right? So when you talk about work, it doesn't make sense to just say how much work is done. You need to say how much work is done by the force of Roy, or by gravity, or by friction, or whatever. And once you've identified that force, to calculate the work, what you do is you take the magnitude of the force, multiply that by the magnitude of the displacement, and then multiply that by the cosine of the angle between those two vectors, right? Okay? And then we learned that you could kind of think of that as, instead of thinking of it this way, we could figure out what the displacement is, and then multiply that by the component of the force that's parallel to that displacement. Or, similarly, find the force and multiply it by the component of the displacement that's parallel to the force. Okay? Big things to remember is work is a scalar. Okay? So it doesn't have direction. You're just going to say how many joules of work are done. The work done by a force is negative if the displacement and force kind of work against each other, right? That'll result in a negative amount of work. Okay? All right. So that's kind of a quick review of what we did, a couple sections ago. So great. But what is work, right? So we spent all this time learning about how to find work, but we really haven't spent any time with learning what work sort of is, right? Which I can imagine was frustrating, all right? So now we're going to tie all of this together, all right? So here's the deal. So remember, law of conservation of energy, sort of in a global sense in science, when we talk about conservation of energy, basically what we mean is that energy can't be created or destroyed. Okay? For our purposes, to break that down into something a little more meaningful, what it means is this. Energy can only be converted from one form to another or passed from one object to another. All right? Now, when we did conservation of energy problems in the last section, basically what we were dealing with was problems in which the energy was converted from one form to another, right? As your roller coaster comes down the car, you're converting gravitational potential energy to kinetic energy, right? And as it comes up, other way around, you convert kinetic energy back into gravitational potential energy, okay? What we need to talk about today is what happens when your total energy changes, okay? So remember, what we learned was that your total energy wouldn't change if the non-conservative forces don't do work, then an object's total energy stays constant, right? So if the work done by non-conservative forces is 0, then the change in total energy is 0, right? Okay? So the question then becomes, well, what happens if the non-conservative forces do work? Okay? So that's when your energy gets transferred from one object to another. Okay? If I do work on an object, then I'm transferring energy from me to the object. If I lift this pen, right, I did work, and I gave this pen energy that it didn't have before, and that energy came from the Cocoa Puffs I had for breakfast. Okay? Similarly, friction, right? When friction slows something down, you're converting the energy from kinetic energy. I guess technically this is converting it to another form. You're converting it to thermal energy. Some of the energy gets transferred to the other object, right? The thing is sliding across. All right, so what we did in the last section was this. We looked exclusively at problems in which the work done by non-conservative forces was 0, okay? Normal force, remember, usually doesn't do work because it's usually perpendicular to the motion, and so our total energy stayed constant. There was no change in total energy. All right, so today we're going to learn what happens if the non-conservative forces do work, all right? And the answer is this. It turns out that the work done by non-conservative forces tells you how much your total energy changes. If I do 10 joules of work on this pen, then I'm giving it 10 joules of energy it didn't have before, okay? If friction does negative 8 joules of work on a box, then the box is going to lose 8 joules of energy, okay? Now, this guy over here, it turns out that the work done by conservative forces is equal to how much potential energy you either gain or lose, but it's the opposite. Okay, so when I drop this pen, gravity does positive work, right? Because gravity pulls down, the pen is moving down. But we're losing gravitational potential energy, right? Okay, so that's what this is, and this honestly isn't a super useful thing in terms of problem solving. But the end result of it is this equation, which is this. It turns out that if you find the work done by the net force, or equivalently, if you add up the work done by all of the individual forces, that'll tell you how much your kinetic energy changes. All right? So it turns out that these two equations here are the jam. All right? These guys are going to make problem solving for us super duper, I shouldn't say easy, but they're useful equations. Okay? All right, so before we get into problem solving, let me kind of show you some intuition behind all of this garbage here that I just put up on the screen, okay? So here's the deal. Look, I want to extend this. All right, so look, net force, by definition, is the sum of all forces, right? So remember, our forces can all be categorized as either conservative or non-conservative forces. So rather than listing all of our forces individually, and this is just sort of some background, you'll never use this in problem solving, but just hopefully it'll kind of conceptually help you tie some stuff together. All right? So rather than listing all the forces individually, let's just consider all of the conservative forces and all of the non-conservative forces. All right? So let's let F and C be the total of all the non-conservative forces, and let's let FC be the total of all the conservative forces. All right? Now, multiplying through by displacement allows us to calculate the work done by these. All right? So imagine multiplying all of these by displacement, so times displacement, to calculate the work. Okay? Assuming that everything is, either parallel or, I guess, anti-parallel. All right? So this would give us the work done. So our net work then, how did I write net work up there? Did I write it with the sigma? Oh, I wrote it as, yeah. All right, so we'll write it this way. So our net work is equal to the work done by non-conservative forces plus the work done by conservative forces, okay? Well, so think about what net force does, right? Net force serves to change, net force causes acceleration, which produces a change in velocity, right? And if your velocity is changing, that corresponds to a change in kinetic energy, all right? So this work done by net force corresponds to a change in kinetic energy, right? Because that net force that's doing the work is going to change the velocity, which in turn changes the kinetic energy, okay? The work done by non-conservative forces is our change in total energy, right? Because those non-conservative forces are not sort of accounted for by forms of potential energy. So if I do work, I'm giving it energy it didn't have before, all right? And then we saw that the work done by non-conservative forces is equal to how much the change in our potential energy, but with opposite sign, right? Okay? So let's see. Now if I add this to both sides, then I get change in total energy equals change in KE plus change in PE, right? Aha! Which makes sense, right? Okay? So, in terms of problem solving, these two relationships are going to be huge. This, net work is equal to change in kinetic energy. And honestly, the one that I use the most, the AP book really stresses this. But the one that I find myself using more often is this guy. All right? So, anyway, those are both very, very important. All right? So let's see if we can apply this to some problem solving. All right? All right, so here we go. So Roy lifts a 5-kilogram box of papers from the top of a desk, which is 0.8 meters tall, and places it onto a shelf, which is 1.5 meters above the floor. How much work did he do? All right, so here's our box. It's a 5-kilogram box. All right, force of gravity on it is going to be just 5 times 9.8, so negative 49 newtons. All right, now we've done problems like this before, right? And so I just want to make a point here. So what we would do then is we'd say, the way that we did this before was we said, all right, well the force Roy needs to lift it is just going to be positive 49 newtons, right? And then we'd just go, oh, well, the work done by Roy is equal to the force of Roy times the displacement, right? So the force of Roy is 49 newtons. Let's see, he's moving it from a position of 0.8 meters up to a position of 1.5 meters. So that's 0.7 meters, right? Difference. Okay? Yes. All right, and so that gives us some number which I was not smart enough to calculate ahead of time. So let me grab a calculator. Clear, 49 times 0.7 is 34.3 joules, right? Okay, so that's that. Okay, now let's break this up into bits and see if we can connect it to some of those things that we were just talking about before. Okay, so let's do this. Oh, darn it. Well, all right, so here's the work done by Roy, right? Let's move this out of the way. Somebody's bothered by that. I'll get rid of it. Okay, now here's another way we can do this. Let's think about it in terms of the energy. Okay, so let's see. So the box initially is at this point at a height of 0.8 meters. And then we lift it up to this point, so we'll call this our height at point A. And then our height at point B is 1.5 meters, right? Okay, so let's do this. Anytime you lift something, you assume it starts and ends at rest, right? So that means that really the only change we care about here is the gravitational potential energy, okay? So if you use the fact that we know the mass and the height, we can calculate the GPE at each of these points, right? So the gravitational potential energy at point A is going to be the mass, 0.5, times 9.8, times 0.8. So that's going to give us 39.2 joules. Okay? And so that was just MGH is all I did there. Okay? Similarly, I can do the same thing up here at point B, and we're going to get 73.5 joules. All right? So, let's see. So that means that because there's no kinetic energy, that means that my total energy at point B is 73.5 joules. My total energy at point A is 39.2 joules, right? So here's a problem where our total energy was not constant. This is super important. Why is our total energy not constant? Oh, because Roy is a non-conservative force, right? And he did work. All right, so let's do this. Let's take a second and figure out how much work Roy did. And yes, we've already done that, but let's do it using some new methods. Or maybe not new methods, but yeah, new methods, using our new ideas, right? So let's see. So for this problem, the work done by non-conservative forces is the same as the work done by Roy, right? Because Roy is the only non-conservative force. All right, and that should equal our change in total energy, right? That's one of the things that we learned just a minute ago, is that the work done by non-conservative forces is equal to our change in total energy. So let's find our change in total energy. That's TE at point B minus TE at point A, right? This is just final minus initial. So 73.5 minus 39.2 gives you 34.3 joules. All right? Aha! That's our change in total energy. That's how much work Roy did, right? We got the same answer both ways. Okay? Now, let's see. Our net force here was 0, right? Because if you, let me see here. No, it's not going to let me do it. All right, so think about what forces were on it. We had 49 newtons from gravity, 49 newtons from Roy. So our net force is 0. That's why our change in kinetic energy was 0, right? We both started and ended at rest. Okay? And you could calculate the work done by gravity, and it would end up being negative 34.3, right? Because we moved to the box up, 0.7 meters. Gravity's pulling down with 49 newtons. So the work done by gravity is just negative 34.3 joules. All right? So anyway, this is a fairly, I don't know, trivial example. I can't believe I just used the word trivial. But the important thing that I want you to notice here is that it is in fact true that our, work done by non-conservative forces was equal to our change in total energy. All right, so let's use this to solve a problem that's a little bit more involved. All right, so what do we got? We got a box with a mass of 40 kilograms. So let's draw this. Here we go. Box, 40 kilograms. It's pushed from rest, so our velocity at point A is going to be 0. We're going to push it a distance of 12 meters. So over here to point B. We'll call this point A, we'll call this point B. Our displacement between those 2 points is 12 meters. We're pushing it across a horizontal frictionless floor with a force of 50 newtons exerted at an angle of 30 degrees below the horizontal. So we'll assume that it's Roy. So here's the force of Roy. It is 50 newtons, and it's at an angle of 30 degrees below the horizontal. So either this or this is 30 degrees, right? Okay. Oh, and conveniently, that's the angle between my force and my displacement vector, right? Okay, and we're trying to find the final velocity of the box. All right, so my recommendation is think about this. Well, okay, so 2 things. Thing 1, let's think about what other forces act on the box. And then 2, think about what types of energy it has at different points. Okay, those are the 2 sort of go-to things. What forces act on your object? What do I know about the total energy at the 2 points? Okay, so let's think about what other forces act on this thing. Okay, I'm going to do kind of a rudimentary free body diagram in that I'm going to label the forces, but I'm not going to worry about sort of how big they are. I'm mainly going to worry about direction. Okay, so we've already drawn the force of Roy on here in red. All right, let's see. Other forces that we're going to have to deal with are the force of gravity, pulling it down, and there's got to be some sort of normal force holding it up. All right, things that I notice is that both of those 2 forces, gravity and normal force, are perpendicular to the motion. So the work done by the normal force is going to be 0. The work done by gravity is going to be 0. But the work done by Roy is absolutely not 0. All right, so let's see. There's no friction or anything. So I think that's it for my forces. All right, so now let's think about energy. All right, so over here at point A, here's what we know. At point A, I know the velocity is 0, which means my kinetic energy at point A is 0. Okay, the height at point A is 0, right? And this box isn't moving up or down at all. So my GPE at point A is 0. That means my total energy at point A is 0. Okay, now over here at point B, I don't know the velocity. That's actually what I'm trying to find. But I do know that the height at point B is 0, which means that my GPE at point B is 0. Okay? So, in order to find this velocity, I need to know this kinetic energy, but I can't find the kinetic energy without the velocity. So, this is what I referenced in the last video as the spiral of doom. Okay? So we need to find that kinetic energy. So, what do we know about the total energy? Well, it's not constant, right? So this is good. So once you get to this point, once you get to the spiral of doom where you need the velocity to find the kinetic energy or the kinetic energy to find the velocity, or whatever, then you ask yourself, what do we know about the total energy? And in this problem, we know the total energy is going to change. So let's find our change in total energy. Our change in total energy is equal to the work done by non-conservative forces, and Roy is the only non-conservative force. So the work done by Roy is his force, 50 newtons, times the displacement, 12 meters, times the cosine of the angle between them, which is just this 30 degrees. Okay? So multiply that out. 600 times the cosine of 30 gives you 519.6 joules. All right? Now, this represents how much our total energy changed, right? It's positive. That means we gained this much energy, okay? Okay, that's how much total energy we gained. So, times the cosine of 30 gives you 519.6 joules. Oops. Times the cosine of 30 gives you 519.6 joules. That's our change in total energy. Okay, so what that means is because Roy was pushing on the box, that's our non-conservative force. The work that he does tells us how much energy we, in this case, gained, right? Because we got a positive answer. All right, so look, if we at point A had 0 energy, and we gained 519, that means that over here, our total energy at point B has got to be 0 plus the 519.6 we gained. Oh, and since the GPE is 0, that means the KE has to be 519.6 joules. Now I can find the velocity. Okay, so this is huge. I just did a whole bunch there. You might need to go back and watch that again if I lost you there, because this is super, super important what I did there. Okay, the work done told me how much energy I gained, which then, as a result, allowed me to find out how much total energy I ended up with. They happen to be the same because the total energy began at 0. And now I know that because my GPE here is 0, these guys have to add up, right? And so the kinetic energy here has to be 519.6. Okay? So now we can find our velocity. So let's see, our kinetic energy is 519.6. That's going to equal 1/2 the mass times the velocity squared. So solve that, and you get 5.1 meters per second. Okay? All right, so that is, oh, I already had the answer. So that is kind of the standard conservation of energy, or sorry, work and energy problem, okay? All right, let's see, what's this next one? Okay, so this one is similar. It's very similar, actually. So you know what I think I'm going to do, and you guys will have to remind me that I need to go over this because I always forget. But take a second, do this problem. Okay, and then, hopefully you haven't looked yet, here's the answer. All right, and then tomorrow, or when I see you in class next, either you'll go, I got it, I'm a work and energy rock star, or you'll say, no, I didn't get it, and I'll go over it for you, okay? I think that's probably makes more sense. All right? Okay, I'm going to skip this problem for right now because it's kind of more of the same. And I want to make sure that we have time to talk about the strongman problem, all right? This is a classic kind of conservation of work and energy problem. So we've done problems where somebody lifts a thing, but let's talk about somebody throwing a thing, okay? So here's the deal. So there is a contest that they have called the Strongman Contest, and they have these big beefy Swedish dudes doing all kinds of crazy stuff. And so this one actually features, it's the Mountain, one of the guys that plays the Mountain from Game of Thrones, if you're a Game of Thrones fan. Okay, so what's going to happen here is this dude here is going to throw this yellow keg up in the air. All right, this thing weighs 33 pounds. All right, he's going to throw it up into the air. All right, there are 3 points that we care about. All right, so the first point we care about is the keg right here on the ground. Okay, when the keg is on the ground, it's got no gravitational potential energy because the height is 0. It's got no kinetic energy because it's not moving. All right, and then he throws it. So the next point that I'm going to care about is the point right when he lets go of it. Right, I'm going to try to pause it at the right instant. Right. Oh, there. Oh, I missed it. All right, so there was a moment right here when he let go of it. All right, at that point, the keg has 2 types of energy. It's got gravitational potential energy because he lifted it up, his height plus a couple feet, right? Plus kinetic energy. So he's actually giving the keg 2 types of energy as he throws it, right? He's giving it gravitational potential energy and kinetic energy. All right? Then, as it goes up, it loses the kinetic energy, and the kinetic energy turns into gravitational potential energy, and then it falls back down. Okay? So those are the few points we care about. All right. I like this problem because it hits 2 super important concepts. All right? So here's the keg. Okay, it starts on the ground. Call this point A. Then Strongman, the Mountain, exerts a force on it and releases it at point B. So this is ground. This is release. And then it goes flying up into the air, stops, and eventually comes back down at point C. Okay? So, between here and here, the force of the mountain, we'll call it M, does work. Right? So we've got a non-conservative force, therefore our total energy changes. All right? Then, between here and here, strongman's not touching it anymore, right? So the only force on it there is gravity. So there are only conservative forces, only, oops, that's supposed to say only conservative forces. So TE is constant. Okay. So let's see what we can figure out. All right. So with all that in mind, here's what we know. We know that at the ground, the GPE at the ground is 0. The KE at the ground is 0. That means the total energy at the ground is 0. Okay? Now, let's see. It says he releases the keg when it's 2.7 meters above the ground. So at this point, here, I'm going to do everything. All right, so this is all point A, right? All right, so for point B, I know the height is 2.7 meters, so I can calculate my gravitational potential energy at point B, right? So it's 15 kilograms, so 15 times 9.8 times 2.7. So the gravitational potential energy there is 396.9 joules. There's velocity at B, and I just don't know what it is, right? That's one of the questions. What is the velocity when he releases it? Okay, so I don't know the kinetic energy at point B, and therefore I don't know the total energy at point B, right? All right, now, also there's point C. Point C is important because that's the top of the path. All right, so at point C, the height is 7.5 meters. So I can find my GPE. So let's see, 15 times 9.8 times 7.5. So that's 1,102.5 joules. The velocity at point C is 0, which means the KE is going to be 0. And so my total energy at C is 1102.5 joules. Okay, so now we know our total energy at 2 of the 3 points. And notice the total energy changed, right? And the reason that the total energy changed is because of this, because the mountain did work from point A to point B. But remember, the only force doing work between points B and C is gravity. So that means that the total energy at C has got to equal the total energy at B. So if my total energy at C is this number, that means that the total energy at B also has to be that number, yeah? Aha! So now I know a whole bunch of stuff. So let's scroll down, give ourselves a little room. Oh, let's embiggen the screen. We got all kinds of stuff to do. All right, so what do we know? Let's see. So first of all, I think if I know the total energy here, and I know the gravitational potential energy here, the difference between those should represent my kinetic energy, right? Because the total energy has to add up, right? So 396 plus something's 1100. So let's see, let's do this. Minus 396.9. So that means the kinetic energy here is 705.6 joules. So now, look at the things I can do. Question A said, what's the velocity at point B? Well, the kinetic energy at B is 1/2 mass times the velocity at B squared. So 705.6 is the kinetic energy. That's got to be half of the mass, 15 kilograms, times the velocity at B squared. So solidify, let's see, so divided by that, gives you that, square rooty, and you get about 9.7 meters per second, which is not bad. 9.7 meters a second, that's, I don't know, 25 miles an hour, something like that, pretty good, 22 miles an hour. All right, so that's the velocity that he had. Now to find the force, well, how much did between points A and B, our total energy changed, right? So the work done by the mountain is equal to the force of the mountain times the displacement, right? because both the force and the displacement are parallel, so we don't need to worry about our cosine. So how much work did he do? Well, how much did the total energy change? The total energy went from 0 up to 1100. So the work that the mountain did is just 1102.5 joules. That's equal to his force times the displacement. Well, between points A and B, he changed the height by 2.7 meters. So that's my displacement, 2.7 meters, right? So divide that. The force of the mountain ends up being 1102.5 divided by 2.7, 408.3 newtons. All right, so there we go. All right, so work and energy, there you go. All right, so here's one last problem to try. Okay, give this a go. And again, remind me, and tomorrow in class we'll go over it. We're going to spend some time on this unit. It's tough. Okay, so there you go. Answer is it's basically 0.4. It's 0.399. Okay, so there's our coefficient of kinetic friction. Or static, I guess, depending on if it's skidding or not. All right, there you go.